Hello folks, today we're going to be talking about number theory. Some background on number theory. Number theory is the study of numbers. And, well, it's not the most application-based study you're going to find. Let's just say that. You're not going to be using the concepts that you learn in number theory, in your everyday life or even in like most careers. But I think it's like the mindset of number theory that's really useful. So I would encourage you to study number theory if you're looking to, solve problems and really get to the heart of abstract thinking. But today we're just going to be talking about two concepts in number theory. We're going to be talking about the Diophantine equations, essentially linear Diophantine equations with two variables, and the Euclidean algorithm, where we're going to see how those two concepts can come together in a really fascinating way. So first, Diophantine equation is an equation with unknowns where you're interested in integer solutions or integral solutions. So an example would be 3x plus 5y equals 1. And you're going to ask yourself, what pairs of x and y can I get to solve this equation? And it turns out there are an infinite number of solutions. But like the most obvious one might be like 2 and negative 1. Which would make 6 minus 5 equals 1. And you can get into like all the different ways to find solutions, but let's move on. The Euclidean algorithm. Now, it might seem unrelated at first. The Euclidean algorithm is a fast way to find the GCD, or the greatest common divisor between two numbers. And it's based on the idea that like as you subtract the smaller number from the larger number and compare that to the smaller number, it's not going to change the GCD. So that means you can like basically make your problem smaller and smaller until it's obvious and you get your GCD back. So let's just run through an example. The the Euclidean algorithm on 37 and 8. So what we do is we take 37 and then we divide it by 8. We say, okay, how many times does 8 go into it? It's 4 times plus, and then we do the remainder. And then we keep on doing that until we get to 3 equals 2 times 1 plus 1. And then 2 equals 1 times 2 plus 0. And this last thing, this 1 right here, is the GCD, so whenever you reach that last point where your remainder is 0, whatever you're multiplying by there is going to be your GCD. So in this case, it's 1, so these two numbers are coprime. And the reason this is fast is because, this is faster than something like prime factorization, which would require testing of up to square root of n number of factors below the thing. So this is polynomial time, which is faster than the other one, which I think is exponential, but don't quote me on that. So the thing is, you can use EA to solve Diophantine equations. So let's dive in. So the first problem is find a solution to the Diophantine equation 16x plus 9y equals 1. So what we can actually do is apply the EA on the two numbers, and then there's a method where you can sub in the different equations that you get from the EA to actually get 1 in terms of multiples of 16 and 9 added together. So we can see here we have our EA performed. 16 equals 9 plus 7, 9 equals 7 plus 2, 7 equals 2 times 3 plus 1, and 2 equals 1 times 2 plus 0. So we can actually ignore the last step, and it's the penultimate step in most of these cases where it's useful, because then we get 7 equals 2 times 3 plus 1. And you only get that plus 1 when these numbers are coprime, which is, something you may have noticed in the last one as well. We had a plus 1 with 37 and 8. But here what you do is you take that 1, and that's going to be the 1 on the side of your Diophantine equation. So take the first three equations, subtract the times stuff from it, so we get 1 equals 7 minus 2 times 3, blah, blah, blah. And I highlighted the things here because you can notice that I can actually sub in the 2 into this first equation and then get 1 in terms of 9s and 7s. And then I could sub in the 7 into that equation and then get everything in terms of 16s and 9s. And that's our solution to the Diophantine equation. So we do out some algebra, and we end up with 1 equals 16 times 4 plus 9 times negative 7, where 4 is our x and negative 7 is our y. And you can check that. That's 64 minus 63, which is 1. So there's our first solution for negative 7. let's go on to the next one. Use your results above to identify a solution to 80x plus 45y equals 30. So they want us to use the results from before. We don't want to just apply the EA here. So let's start with our equation that we got. 1 equals 16 times 4 plus 9 times negative 7. And what we could do is we could scale this up by 30, so we get 30 on one side at least. So that's 30 equals 30 times 16 times 4 minus 30 times 9 minus times 7. And then we could actually split that 30 and do something a little clever. We can place the 5 alongside the 16, make that 80. We can place the 5 alongside the 9, make that 45. And now we have 80 times something plus 45 times something, and that is our answer. So that turns out to be 30 equals 80 times 24, which is our x, plus 45 times negative 43, which is our y. So that is how we got the answer to our second question. Now our third question is find another solution that minimizes the relative size of x and y. Then use this solution to provide a set of instructions for how to cook a 30-second egg using only an 80-second timer and a 45-second timer. So we're going to do the math of this in this video, and in my next video, which I actually already published, we are going to do the timer experiment. Just a little background on the timers. The timer philosophy is actually the same as this. What you're doing is, I have an 80-second timer. I'm going to stack a bunch of, I'm going to like run that 80-second timer a certain amount of times, and then I'm going to run the 45-second timer a certain number of times. And basically, I'm going to find a place where the difference between them is going to be equal to 30. And that is directly equal to this. If I run my 80-second timer 24 times and my 45-second timer 43 times, what happens is the difference is going to be 30 seconds. And then basically between those two timers, I can cook my 30-second egg. Obviously, you shouldn't cook eggs for 30 seconds, but you get the point. So let's do the math. So we have x is 24, y equals 43. Those are big numbers. I don't see some clever way to manipulate this as before, so we should just go back to the EA and try something with that. So we do our EA, we get 5 as the GCD, 80 equals 45 times 1 plus 35, 45 equals 35 times 1 plus 10, and blah and blah. And what we can do is we can take the penultimate equation as we did before and scale it up by 6. But, you know, I think there's a little more clever step where you can look at the second equation and you have 45 equals 35 plus 10, and then you could just start with that 10 and then scale it up by 3. So instead of having to scale up 5 by 6, we scale up 10 by 3. So that will minimize the relative size of x and y in the end. So let's start with our 10 equals 45 minus 35. And then we can also manipulate the first equation, get 35 in terms of 45s and 80s, sub that in, and then we end up with 30 in terms of 45s and 80s, and we're good. So the answer turns out to be 30 equals 80 times negative 3 plus 45 times 6. So basically we have to run our 80-second timer 3 times, and then at the end of those 3 times, we are going to, our 45-second timers are going to be running simultaneously, but then between the end of those 80-second timers and the end of the 45-second timers is our 30-second window. And next video, we'll see how that turns out. Thank you.